Before we start the next session, we are planning, assuming it's not pouring with rain outside, at the end of this session to have a photograph outside. So if at the end of this session you can just sort of stay here, we will make it clear what's going to happen. I'm not quite sure what's going to happen, but something's going to happen after the end of the session. So you can stay rather than run away to lunch or whatever. Well, I'm sure everyone will want to stay completely to the end of your talk again, but if you can stay, that'd be great. Thank you very much. Now I'll hand over to Ryan, who's going to...
Okay, so welcome to the second part of the morning. It's a pleasure for me to announce the talk by Sophia Ohlhede from University College London and the title Modeling Non-Stationarity.
Thank you very much, Rainer. So hopefully you can hear me at the back. I managed to switch on the machinery correctly. Okay, great. So I'm going to talk a little bit generally about modeling non-stationary processes. There's more towards that rather than the change point work we've seen earlier today. This is joint with various co-authors. Bits of it is with Ananda Ombao. All of the clever bits is with Adam, who will also be speaking later in the week. So if you see something particularly clever, it was probably Adam's idea, and if it's particularly stupid, it was probably my idea. So I'm going to start off by talking a little bit about modeling non-stationarity in general, and this will harken back a little bit to Rainer's plea for general frameworks to understand non-stationarity, and also go back to things that Guy was talking about. What happens if you use different representations, if you don't want to use an assumption of stationarity coupled with a Fourier transform. I'm then going to talk about using frequency even if you don't have a stationary process and what we can say in such scenarios. And then I'm going to move on to what I actually promised to speak about, which there's going to be a little bit less of than intended. And I'm going to talk about bivariate models in time frequency and frequency. So just to recap, I mean, everyone knows the basics here already, but just to make sure our notation is all set up in the same way, we're going to start by looking just a single time series. If we want to assume the series is Gaussian, if we want to know everything about this series, we would just have to understand its mean, which in general would vary with time. And we would want to understand its covariance across time, which we see there in equation 2. Maybe if I'm really clever, I can even use the pointer. Yeah. And we're going to assume the mean is 0, and we're going to try to describe that evolving dependence between points of the series at different time points. And again, as people have already pointed out, stationarity is a nice and constrained setting. Non-stationarity can happen in many different ways. And here you just see some different examples of stationarity, what I would call time-varying non-stationarity, in that you're multiplying a stationary process by a deterministic but time-varying function. Something that's too smooth to be stationary, and a cyclostationary process. So I'll talk a little bit about these types in a little bit. So just to recap, what is it we actually want to change? What do we have as our tools of the trades that we can work around with? Well, how would we know initially if we had a model which was actually valid? So before we start to propose lots of different new models, let's just recap. What do we actually need to model and what constraints need to put in there? So in general, if we have a zero mean process, we would just want to understand the autocovariance sequence across time. And we would need that matrix for the observation, which has all the different covariances listed in it. We would need it to be positive semi-definite, because otherwise it wouldn't be a valid autocovariance or a valid covariance structure. So in general, when we propose models, what we have to worry about is that we need to check that we're proposing models that are actually valid covariance structures. And once we've done that, the second problem is I can propose models until the cows come home, but if I can't estimate them from a single set of realizations, they're not going to be very useful to people. So in total generality, this is too general, and we need to think about ways of proposing families of models that give us autocovariance structures that have the right properties. And the standard answer, which we're not really here to apply, is just stationarity. Shove in a constant mean and let the dependence structure not change over time. And what you would then have is a description of the dependence across lags, but it would be the same across time. And you could take its Fourier transform and look at its spectrum. So we're just about to move on to new stuff. I'm sure you can all start to wake up, because you will know everything about non-stationary time series already. What's the implication of having all of these things? Well, the first thing is if you have a stationary process, Normally, it's just a good idea to average across time, because you might as well pick up those degrees of freedoms. Secondly, you can write down the process just as a weighted average in frequency, where you're putting zero mean weights on each complex exponential. And you then start to describe things in terms of the spectrum. I'm a little bit naughty. I've assumed here that the spectrum is absolutely continuous. We're not going to worry about that. And if you start to move away from that, if you go to traditional theory for non-stationary processes, you start to say, well, X is changing a little bit. It's not changing too much, because then we can't make it out. And you start to say, instead of having a spectrum, I'm going to have something that's indexed by a little t there, which is starting to change very slowly. And one of the main repercussions of this fairly innocuous and harmless assumption is that you'd think that if you calculated the Fourier transform, if you did this representation, but no longer for a stationary process, you'd start to really mess up the correlation here if you started to make this very unsmooth. So as long as this remained quite a smooth function in time, you'd expect these different weightings in frequency to be nearly uncorrelated. So let's have a look at some real data. So this is some electroencephalography data, and this is the time when it apparently appears to be de rigueur to claim that you're working with Ananda and Bao. So I will do the same thing. So this is some EEG data that Ananda and I have been analyzing. And we have two different estimates of correlation across frequency. We've averaged quite a bit, you can see that. But on top of that, what you see is a measure of correlation as you go across frequencies. So that's frequency 1, frequency 2. And what you see is some considerable correlation off the diagonal. So you're seeing big kind of islands of structures that are indicating frequency correlation. Now, a classical locally stationary model would not give you this, because the smoothness in that time would allow you to blur things out a little bit here. But then the smoothness, I mean, say you put in something like Sobolov or something like that, the smoothness would then force you to have a rapid decay as you went off the diagonal. So this is real data. Problem number one. Traditional frameworks don't work. I can't use the assumption of local stationarity because we have significant off-diagonal correlation. So that kind of goes back to Guy's plea for new frameworks to analyze non-stationary time series. Well, we don't actually have to do something new here, thank God. We can just go back and say, okay, I like this whole notion of writing X as a mean, which I shall now make time varying. And I like these complex exponential things because they're neat functions and they often do cool things. But now I'm going to take this random weighting that I'm giving each frequency, and I'm actually going to make them correlated, because that seems like a sensible thing to do, because my little estimator here, which I'm going to explain why it's sensible later on, is actually showing you that there is a lot of correlation of the main diagonal. So assuming uncorrelatedness would seem pretty dumb in that setting. What can you do then? Well, you can say, if I'm looking at correlation, I need to define an appropriate measure of that. I'll start off by just saying that the covariance of this random weight is going to be the Löw spectrum. And if I want to remove the magnitude information, because I don't want to be tricked by the fact that something's happening at the frequency, I'm going to standardize it in a fairly normal way that you would with any correlation or covariance. So now we have a new measure, which is basically telling you how correlated are the processes at different frequencies. So locally stationary methods won't work here. Things will fail. What can we actually do in this setting? Well, we can look at these mathematical structures and we can say, great, we now have a new framework which allows me to model, but how am I actually going to do estimation, right? Because it's all very well to write down models if we can't estimate them. Well, we can interpret the model before we go on to estimation. We can actually see that if there appears to be correlation, we could think of that as having that random weight at one frequency depending on the random weight at another frequency. And you'd also need to look at the complex conjugate, because these weights are all complex valued. So we could start to think of these frequencies being linked. There could be effects such as phase locking, where you have frequencies that are apart by a certain distance being forced to always appear together. So that looks like quite interesting. We could interpret the models. It's all looking very cool. But we then pause and we think, not that good. If we want to estimate this whole function here, and we use the usual grid of Fourier frequencies, we've got too many things to estimate. We've got as many things as we would have to estimate when we were looking at the non-stationary autocovariance function. So I'm now going to take a little aside and ask ourselves what other things could we have looked at before I'm going to propose a way of actually estimating this function. So we started off by just looking at the autocorrelation or autocovariance function in time, which just described across time how do the correlations across different lags change. So that's very much a temporal description, and people have proposed to do estimation, but for most of these methods to work, you have to assume that you have multiple replicates. You can't just have one time series and then do the estimation, because it's just too overparameterized. We've seen people talk about the Wigner distribution, which is basically a Fourier transform of that autocorrelation function. And that people have also discussed estimating in various scenarios. People have used sparsity assumptions. For instance, Borgnet and Flandrin is one of the references here. We could also take a Fourier transform here in terms of that T and end up with what's known as the ambiguity function. That's another representation of the same autocovariance sequence. And I worked with a Norwegian collaborator in estimating that, again, using sparsity assumptions. And finally, today, what we're going to talk a little bit about more is estimating correlation structures in frequency. So in a sense, what people have been doing most of the time is estimating quantities related to the Wigner distribution, because local Fourier transforms are cousins of the Wigner distribution. People have looked a little bit at doing time domain estimation, because if you use time-varying ARs, you're firmly in that setting. But there is a whole plethora of ways of understanding time series, which, like Guy says, give you a different lens to see the structure you're willing to investigate. And what needs to happen here is exactly what Rainer was talking about. We need to have general frameworks and general models so we can evaluate, once we get procedures, if the procedures are going to work well or badly. They're all representing the same sort of structures. They're just different views. And it's easy here to get a little bit confused, because there's a lot of signal processing literature where people think that if you take different kinds of these different distributions, they're actually all estimators of each other, because they can be written as convolutions or linear transformations of each other. And there you have to be a little bit careful, because usually these convolutions don't stabilize variance at all. So you're just transforming a bad problem into another bad problem. So variance is the main enemy here, because you have too many quantities to estimate and not enough data. Modeling is also very difficult, just to take a step aside. I mean, what's really nice about stationarity is that it's extremely easy to check if you have a valid model. If you write down a random choice for any of these functions without any sense, it's impossible to determine whether you have a valid model, right? If you enumerate the autocovariance sequence in a matrix, you can check its eigenvalues. But if you want to write down general parametric models, it's impossible to know what parameter values are going to give you valid models. So I'm just going to give an example in one of these different domains in how you might approach this problem. And given, it's a little bit old-fashioned now, but given sparsity has been the popular way of reducing modeling problems, I'm going to take this line of thought. So we're now going to be modeling things in frequency. And in frequency, you need to be a little bit careful, because the easiest thing there is not to think about absolute frequency values, but relative frequency values. So we're going to start out with absolute frequency values and start to model. So the classical way of introducing, and this goes back to Gladyshev in the 1950s, at looking at correlations in frequencies, is to say the correlation between frequency 1 and frequency 2 is just an aggregation of delta distributions where these need to be spaced a certain distance apart, then you'll have correlation. And that's a cyclostationary process. And if you look at its covariance across a time and a different lag apart, then what you get is exactly cyclical processes. And a little bit later, people generalized this to not just having lines that was F1 is F2 separated by C over D, but they looked at general forms of correlations in the frequency domain, which are extremely sparse and correspond to coupling of different lines. So that's kind of a classical framework. And again, You can do estimation simply because instead of having to estimate something which you need to make a little bit smooth, but then only on a line, you have something which you make a little bit smooth on several lines. That doesn't really change the inherent order of number of parameters. So if you want to think about the geometry of that model, what you just have is, if you think of a given set of frequencies, whenever you put something at a given frequency, it's going to cause lots of support in correlations, because you can't just put in a value of a presence at a certain frequency without introducing a lot more of correlations across many frequencies. So if we put a peak given at that frequency, then there has to be correlation with the frequency and itself. That's when you're on the line. And then if you put in other peaks, you'll get a plethora of dependencies which have to be there and explain these models. So if you just did a simple non-parametric estimator of that correlation, you would expect to see large correlations at lines with the given spacing. And the fundamental parameter to estimate here would be exactly that spacing, because it would tell you about the periodicity of the model. Unfortunately, real data doesn't look like that. So again, this is some of Hernando's data, and I'll talk a little bit more about it later on. And now I've done sophisticated smoothing, so it doesn't look as blocky as before. But what you see is just not lines, but whole structures, which, yes, show some coherence in their geometry relative to the diagonal, where all of the stationary stuff would be living. But you see a lot of different correlation islands as you go across. So it's clearly not enough to just have models which give you support only on the lines and the diagonals with a certain spacing. Real data seems to have more structure. So, okay, the first alternative now is to say, Hernando, your data is horrible, take it back. I'm not going to do anything with it. Well, that didn't really seem like the first alternative, because Hernando is such a nice guy. So if you want to try to understand what's going on when you get correlation across more frequencies, you have to ask yourself, why is this happening? So you remember before we were talking about the correlation at a certain time at certain lags. We start across this model, but we say, oh no, we don't want this simple structure which just has a certain weighting to certain lags with additional periodic structure with a given period d. We actually want to have variation of that periodicity within the time interval that we're looking. So we take this very simple cyclostationary model which enforces correlation at certain periods, and we say, yes, those periodicities are part of the data, but the way they appear is going to change across the interval we actually observe the data. So why do I do this? Well, basically to spread the lines, because of the way time and frequency interact. To make it more spread in frequency, I'm going to have to introduce inhomogeneity in time. So I'm sort of backwards guessing, how am I going to make up structures which look like what I've seen in frequency? Things that are rapid and narrow in time are broad and diffuse in frequency, and so I'd have to introduce some time variation. So we can think of this as an amplitude which is modifying what importance you're seeing in this correlation as you go across time. And if you start to rewrite the correlations across frequency, where I now talk at correlation at the given fixed frequency f with an offset of nu, and rewrite it into components that are made up from Fourier transforming each of these elements, what do we get? Well, we get a correlation across frequencies, which is the Fourier transform of what we had up here, which is exactly a smooth function showing some blurring. So that temporal variation that we're introducing to the correlation structure is blurring out the shapes in frequency, which is exactly what we saw from my non-parametric estimator. And as I said again, it's easier in frequency to think about being at one frequency and then looking at shifts away from it, because all stationary models would have a delta of nu in them. So, okay, what have we done now? Well, we can think of having little islands of support in frequency, where the support and how widely it spreads is governed by how much we make things vary in time of these periodic structures. It seems quite simple. I could just write down functions which gave me this diffuse correlation structure, but we have to be really careful, because Again, we're modeling covariances. I'm not allowed to just write down a covariance structure and say it's valid, because if I shoved it all into a big covariance matrix and calculated its eigendecomposition, I would end up with negative eigenvalues, which would lead to negative variances, right? And then I realized I was stupid. And I'm telling you this because I did this by mistake once. So, there is nothing like practice. It's pretty stupid, actually. So to go back, we now have a model which is actually capable of thinking about structure which just describes power or values of large and important frequencies across frequencies. And I'm now starting to think of models which allow me to, off that diagonal line, describe diffuse structure depending on how variable was the function actually in time. The question then comes, can we construct such covariances? So I happily wrote them down for you. Can they actually be constructed? Well, here it's easiest to actually make up an approximate argument because it's easier to understand. So one possible way of actually constructing such a structure is to take a single stationary time series, multiply that time series by a time-varying function, and then shifting that in frequency to giving a little bit of frequency correlation in that Löw spectrum. So you can sort of making it up by taking a single time series, shifting it a bit in frequency, and then introducing time variation in its power. And if you go through the calculation, you can calculate the autocovariance sequence. It's quite ugly, but what you find is that in simplest case, where you simplify how you're modifying it in time, you can actually end up with covariances which nearly have the time-varying form I described. So I only give you this example to show how you might approximately construct such covariances. Going into the exact case would not be nice here, so I'm not gonna. Well, that's all very well. So now I've made up a structure. I can make it up. I can make it up from an actual set of observations, so I won't end up with negative eigenvalues. Can I actually estimate it? Now, here I'm going to cheat. So Ananda was very nice to me. He gave me repeated observations of the types that we saw yesterday. And we're going to be using these replicated observations to actually do the estimation. And I find modeling replicated time series very interesting because some of the early papers I talked about, they all assume that you get a new replica which is identical to the processes that were generated before. And I think one of the most important things here to do is to make up a realistic mechanism of replication, because you never see things from exactly the same distribution. So we're going to have R being the replica. We're going to have a XR being a collection of time series from that replicas. And we could have assumed the replication is perfect, i.e. that we would get samples from exactly the same distribution. But in real life, it often turns out that you have a mixture of distributions. So I'm going to think that that replica is actually generated as a mixture with some M distributions that it could have been sampled from. Now, this is not good enough. Even starting out, you might think this problem would describe what's going on quite accurately. One of the big dangers of using a simple model here is it doesn't really deal with phase shifts and delays. So the kinds of neuroscientific time series I'm going to talk about, these are incredibly important characteristics, and they're often a very little bit different across all replications that you have. And I'm going to explain why not dealing with them is going to make you very, very unhappy, but it's not enough to just say you've got a population of distributions. We need to model a little bit more. So I'm going to be using two different things here. I'm going to be thinking of an overall time shift. So when I get my replicates, where I start in the process is going to vary a little bit. And this is particularly adapted well to neuroscientific trials, but there are other scenarios where it's realistic as well. And then I'm going to assume that the time series also have all of these cycles part of it, and these cycles all have a phase shift which tells you where in the cycle you're at, and each replica is going to have a slightly different phase shift. Now this might seem like incredibly complicated. Why do I want to take my replications, shift them a little bit in time, and then introduce phase shifts? Well, I basically have to do it to make the analysis work, because in real life, you do not observe things perfectly in synchrony. things start a little bit different every time. So we can think of these time shifts and phase shifts as synchronizing the structures, and we can think of having synchrony across the whole observation and synchrony of the components that are parts of the observation, and both of them are very important. And what's the effect of introducing them? Well, if we think about the common covariance that we see across replica R, when you got the component from that mixture you saw on the previous page, which is M, you're going to get a complicated form. Don't look too much at the formula, as Chiu I said yesterday, but you're going to get a structure which has some kind of magnitude associated with it, an amplitude function which has been shifted in time depending on where you started, and some idiosyncratic phase shift which could really mess things up. So the reason we need all these bits of the model is that in real data, these are often present, and if you ignore them, your estimation procedure is going to be bad. So having sat down and figured out that this is an appropriate covariance, you can actually calculate how each contribution there is going to give you a typical Lairve spectrum contribution, which unfortunately inherits all of the different phase shifts. And the annoying thing there is that if you just try, when you get all of your replicates, if you say, okay, I actually think there's no mixture, I think there's only one component which could be present, and I'm just going to average. The problem is if you've got complex valued things and you average across things that are not in phase, is that you're going to get very, very noisy estimators, and you're not going to be able to recover things very well. So if you look at this, because of the fact that they have a very specific support in frequency, that it's only non-zero for some values of nu and m, you can actually argue that the magnitude of this quantity is actually like a sum of magnitudes, and you can get rid of the phase shifts by just taking magnitude. So this is not very precise either, but that's the idea. And just to show you what difference it makes when you start to use the methods, whether you look at magnitudes or not, this is looking at the covariance across the two different frequencies when you've looked at magnitude and removed phase shifts. Keeping the phase shifts in kills off a lot of structure when you start to combine information across different trials. So we now want to estimate these structures. We want to understand all of the components that are present in the data. And what we can do as a first go is just to see how, if you recall, this was the magnitude of the cross-correlation in frequency. We can use our model and see how that would actually relate to the different parameters we set up. There are a little bit too many parameters, so I'm going to skip over this quite quickly, and then we'll actually see what it looks like in real practice. We could think of trying to represent this magnitude function across different frequencies, and you could think of doing a basis expansion, for instance, to simplify your estimation. And with that assumption, you can actually shove through the maths, and what you get is that what you would observe is going to be a representation where your replica, what mixture you're at, and which series you're at, you're going to get, or which basis function you're using. You're going to get a weighting which is associated with each basis, and that represents your overall magnitude or correlation across different frequencies. And we can think of that coherency, therefore, for replica R to be described well in a basis expansion. And I think you all probably see where I'm going now, because, of course, we now need to estimate things, and we need to simplify what these descriptions across all of the different trials give you. So again, we're going to do something very simple just to start with. We're going to start off by just calculating raw cross Fourier transforms, multiplying them together like you would a normal correlation measure. And then we're going to average them across all of the different replicates. And what we actually get when we average the magnitudes is a measure overall of the magnitude of the correlation between different frequencies across different trials. And we're going to be implementing this using tapering. So we're going to get a different independent realization from each tapering. And that's going to give us an estimate for each replica of how correlated the different frequencies are. So it's quite non-parametric as of yet. We need to assume a little bit of smoothness in the Fourier domain, but otherwise this is perfectly fine as an estimator. We're going to sample all frequencies. We're going to create the vector. We're going to make up a huge matrix containing all of these estimates of correlations across all of the different frequencies, across all of the different subjects. So what we have now is a non-parametric estimate of the correlation across all frequencies, across all of the different subjects. And of course, we can do eigenvalues or singular values to actually try to estimate what this correlation is like. And what is that singular value decomposition going to give us? Well, we're going to see similar shapes in dual frequency, which is going to correspond to the vectors UK. But we have to be a little bit careful because, of course, this big matrix that we construct is going to be tremendously noisy. And we all know that doing singular value decompositions of noisy matrices that are very large is a really bad idea. So before we actually do a singular value decomposition, we're at every frequency going to test whether something is noise or not. We can use the assumption of stationarity to remove things which are there purely by random variation. And of course, we need to be conservative, correct for multiple testing, because we're calculating a large sets of correlations. And we don't want to retain lots of noisy induced correlations. So we can just take that raw matrix of all the correlations and threshold it using the distribution under stationarity and correcting for multiple testing. So let's see how this is done. Here we have raw estimates of correlations for two different trials. We see they look quite different. That's why I wanted to have the availability of several different covariance forms that could be present in the data. So this would see a lot less time variation across the trial because things are a lot more narrow in frequency. This would have seen a lot more change of the subject's response across time because the structures are more diffuse in frequency. Once we threshold, a lot of that structure was not significant, and we end up with simpler matrices. So we then have a thresholded matrix. We can calculate the trial-specific vector. We can calculate singular value. And we can actually get an estimate of the actual frequency structure or correlation using the singular value decomposition. And we're going to be looking at the singular values to determine how many of these we need to use, just like anyone would do. And we're going to describe how different are the different trials by looking at using k-means on the trial-specific vectors. So we're now going to go back to the data example. We've actually got the EEG data. What's really nice about analyzing EEG in frequency is that frequencies are important. People actually describe things like delta brushes or different phenomena in terms of their frequency support. In EEG, there is no reason to assume stationarity, especially if the subject experiences stimulation at the start of the trial. And there is linkage of frequencies, as we've already just seen. So having done that, okay, having calculated the matrices, having thresholded them, having made up a huge matrix and calculated the singular value decomposition, what kind of correlation structures come out in frequency? Well, here are the first 4 singular vectors which show you what typical correlation structures they're at. So we're seeing some off-diagonal with a fixed frequency apart, which are linked with a certain type of response. We're seeing a structure which removes some of that correlation. That's actually going to be used for some of the trials to you subtract some of those correlation structures to get back some of the other trials. And once you start to go into higher values here, basically you're getting idiosyncratic effects associated with each trial. And what actually comes out is that only the 2 first vectors are needed to describe the covariance form. And if you look at clustering the weights, you actually have 2 typical states. And what happens is, as you go across the different trials, you switch between these different states, and you can use the magnitude of state of the first 2, 3 vectors to determine which state are you actually in. And it turns out that most of the trials either show very little correlation across all of the different frequencies, or a lot of correlation indeed. So we're having very synchronized forms which just have a few set correlations versus a lot of diffuse spread structure which happens in between the other states. And as you go across time, what you see is that there is also a change in that there is more variation to start with, and then it sort of locks down to being a simpler description across time. So there are clear non-stationary features here. There is correlation in frequency, and I think of this as frequency coupling because it's forcing certain frequencies to occur together. I kind of ignored the phase characteristics. I killed them off, and that's because estimating phase is very hard indeed, so I choose not to. So that's certainly work that needs further efforts in order to actually establish what's going on. The magnitude of the coherence is quite replicate across time, but not perfectly so. And we see two different types of sort of correlations between different frequencies, one which is quite diffuse across frequencies, one which is very well spread, and that's going to have to do with how the correlation changes in time, and is something I want to look more at as well. So I now have 5 minutes, and I'm going to talk very, very briefly, and I'm going to get stopped at some stage, in which case I will make a ladylike stop, I hope. So we've looked at the correlation of frequencies for single processes. If you have more than one process, there is room for a lot more structure. And the structure in the frequency domain becomes more complicated. And Adam, my postdoc, is going to talk more about this tomorrow at about 4. But I thought I'd give you a little bit of a background on what can happen when you have more complicated structures. So those who know me know I've been working with oceanographic data and the big global drifter program for many years. And there, our big overarching aim is to describe all of the variability you see in different time courses that correspond to a change of location of a drifter observation as you observe it across time. And here's just a given example, which is coming right from there. And I'm going to just give you a brief feeling for what can happen. So when you go bivariate, the natural thing is to reach for being complex valued. And that means you want to write down a complex valued function in terms of its Fourier decomposition. But of course, compared to all of our normal understanding, the Fourier decomposition no longer have to show Hermitian symmetry, because when you're calculating Fourier transforms of complex valued quantities, there is more potential structure. And something that's very convenient in oceanography is to start to try to decompose these frequencies in terms of structures that's associated with positively rotating phasors and negatively rotating phasors. So if the quantity you're observing, if you take one step back, for instance, if it's circling round clockwise or anti-clockwise, that's going to lead to structure happening associated with the positively rotating or negatively rotating phasors. So one of the interesting things to understand once you start to have complex valued structure is how do the different frequencies interact or link as you start to observe a phenomena across time. So the big generalization here is that you have a whole set of extensions to way of modeling which was not available to us before, because now we have more degrees of freedom, we have negative and positive frequencies, and the structure of that joint phenomena describe what's going on across time. And I think rather than going into the rest of the end bits, I'm going to stop here and suggest you go to Adam's talk tomorrow.
So, thank you very much for the talk. Are there questions, comments? Actually, I have a couple of questions. The first one, can you please go back to was about the third, fourth slide where you said this is all about the same covariance object, all about the same matrix. You have the 4 methods, right? And then you...
Let's see if I can... Yep, there we go.
I find... Could you show the matrix, please? One slide back. No, 2 slides. Oh. There it is. I mean, this is... Perhaps I can show this. The point is what I think what you could do, and this is my question, but also a suggestion. I mean, when you take the definition, you could say, I mean, you have the covariance, say xt plus tau, I think was it xt, and
yes.
The definition was that was c tau t, correct?
Something like that, yeah.
Yeah, but what you could view it that I mean you assign it to the time point at one edge. So you could assign it to the time point in the middle.
Yes.
And then you would say, okay, basically this is t plus tau half or something like that. It assign to
Yes.
that time point.
So
And then the point is you get the structure of the matrix where you basically have the correlations in this direction. This is so I'm excited because I was thinking of the same matrix yesterday or two days ago.
maybe
So basically you have correlation is basically correlation of like 1 is here, 0 is here, 2 is there. And then you have somehow time is in this direction. So basically this is t, then you have t plus 1 and so on. And so you are perfectly right in your comment that in locally stationary models, when I've been investigating this matrix, and a lot of my work is on that matrix as well, I rule out the effects you are describing. I mean, by the assumption. So I completely agree with that, and I think it's very important to look at these things. But what I find exciting there are really to look at this matrix problem as a matrix problem. And so I think we have complete agreement on that. And I think this is a very exciting point, right? And
But there are some problems as well when you start to do those small shifts. So you might be familiar with work by Matz and Lavach in signal processing, where they define processes where things are not allowed to jiggle too much depending on how you do the offset. So they basically assume that the ambiguity function has to be compactly supported in a small domain around the center. But that causes a lot of other issues, and I think a problem here is in signal processing, when you describe these representations, you confuse variance, which is there due to sampling variability, and the mathematical properties of the representation of the covariance function. So they confuse these two effects, and when they see irregularity or nastiness, they think it has to come from the variance. But depending on how you define your process, you're going to get mathematical properties associated with how you choose to sort of represent or define this object. And I think the important thing is to come up, like you said, a framework with a model, so that when you choose a certain representation, you understand what properties it has. And you understand that if you choose a different representation that has better mathematical properties for some class of function, that doesn't do anything to the variance. It just changes the way you're transforming that matrix. And that's a deterministic operation, which has nothing to do with estimation. And because those deterministic operations are all convolutions, people confuse it with estimations because they're used that convolutions are there to stabilize variance. So I think the bigger question is, how can you come up with general frameworks so it makes sense to use a certain sort of integral operator on the continuous non-sample version of that object and understand both the variance and the representation at the same time.
And I have one more question. Could you show your beautiful plots basically with the correlations of the frequency? Yeah, that for example. I mean, the question is the following. If you take these spectral representation, with which you start and where now the frequencies are dependent, right? So typically this representation is not unique, right? I mean, you have a non-unique representation, and then you take the correlation of these components. Is there any way of thinking that this representation could be invariant to the different? So if you have the same signal, you take two frequency representations, take correlations. Could you somehow say this plot is invariant about this, or this plot is unique despite the fact that the spectral representation is not unique or something like that?
This plot is sort of unique because it's just it's trying to estimate correlations once you've taken Fourier transforms, and there is just one Fourier transform. The problem is before, when I defined the amplitude modulation on the components that I was writing to create, where it's being generative rather than analyzing, I could make up different generating mechanisms that would lead to the same object here. So that's the problem. They would have exactly a need for constraints like you do when you have your amplitudes in your variant of the spectral representation. Those amplitudes would also need constraints in order to be identifiable. But I mean, this is the beauty of the Fourier transform, is there is only one Fourier transform, and if you calculate the Fourier transform, you can always define the covariance. Well, as long as it's not too nasty.
I agree, yes, of course.
So that's the beauty. The ugliness is that often when you do something local in time, it's more interpretable. This has mushed up. So I talked about the variation in time of these components. It's taken all of that structure and mushed it up into a broad object. And that's the ugliness of frequency compared to the time frequency models you study, because they're more precise.
And let's thank Sophia.
One thing that's been observed in the study of neuronal time series, I believe it's on spatial navigation of rats, that you have your alpha wave going, and then at the peak of the alpha wave, you have a burst of gamma activity. And so in other words, that you have correlation between these frequencies. And I think that that's what's happening here. Exactly.
Something like that, yeah.
Yes, exactly. I think that these models that you're proposing with the dual frequency models is very good for these types of studies. From a methodological perspective, though, so that alpha gamma locking has been observed so many times, and so perhaps depending on the study, instead of say testing each element of that correlation matrix, just mask it, and only on those frequencies that you're interested in, will probably help out your estimation procedure a lot more, especially since you won't have as many multiple tests to consider.
I sort of didn't talk about this, but I actually didn't do multiple testing across all frequencies.
Oh.
So Hernando told me not to. So I actually only chose a set of frequencies we were interested in first, and then did thresholding on that. So you're precisely right. And I can't take credit for it either. It was Hernando's idea. Okay. Thank you.
Any more questions? If not, then let's thank Sophia.